every one of you can see the screen. So today what we are going to do is, we are going to prove that in a triangle, the angle bisectors of a triangle are concurrent and the altitudes are concurrent, the perpendicular bisectors are concurrent. Okay, so we are going to prove that these three things are concurrent. We have already proved that the medians in a triangle are concurrent at centroid. And if time permits, then we'll also see the rest of the quadrilaterals. We have already covered what are parallelograms, then we'll see what are the other quadrilaterals. Okay. So before proving those things, let us do a simple question. So if P lies on perpendicular bisector of line segment AB, then prove that P is equidistant from AB. Then prove that P is equidistant from AB, from A and B. Okay. So this you need to try. Very simple question. Do it quickly, then we'll discuss. And so let us discuss this one. We are given a line segment AB, right? And P is a point which lies on the perpendicular bisector of AB. So what do you mean by perpendicular bisector of AB? It passes through midpoint of AB and it is perpendicular to AB. That is the perpendicular bisector of AB, right? So this is the perpendicular bisector of AB. Now say P is a point on the perpendicular bisector. So this is 90 and these two things are equal. Say this point is D. We need to prove that P is equidistant from A and B, right? So we need to prove that PA is equals to PB. This is what we need to prove. Fine. So now if you see the triangles PAD and triangle PBD, you can notice that these two triangles are congruent triangles by the SS property, because AD is equals to DB and this angle is same, that is 90, and PD is the common side. So triangle PAD is congruent to triangle PBD by SS criterion. So this implies that PA must be equal to PB. Okay. So if P lies on perpendicular bisector of AB, then P is equidistant from both A and B. Also, I can say that every point on perpendicular bisector of AB so is equidistant from A and B, right? So every point on the perpendicular bisector of AB is equidistant from A and B. So these two statements are equivalent, right? So now let us prove the converse of this statement. What will be the converse? Converse is that if P is equidistant from A and B, if P is equidistant from A and B, it means PA is equals to PB is given. Then you need to prove that P lies on perpendicular bisector of AB. So you need to prove that P lies on perpendicular bisector of AB. So I'll give you 30 seconds to do this, then we'll discuss. So if P is equidistant from A and B, we need to prove that P must lie on the perpendicular bisector of AB. So let us do this. Say these are 2 points A and B, and we have joined AB. So this is the line segment AB. Say P is a point here, fine, and it is given that PA is equals to PB. So these two are given equal. Okay. So we need to prove that P lies on the perpendicular bisector. So let us drop a perpendicular from P onto the line segment AB and call this point as D. Okay. So drop a perpendicular from P on the segment AB. Fine. Yes. Now, if you observe these two triangles, PAD and the triangle PBD, these are congruent by RHS because these two are right angle triangles. Hypotenuse is equal in both the triangles, and this is a side which is common to both the triangles, so it is equal. So I can say that triangle PAD is congruent to triangle PBD. So this implies that AD is equals to DB, right? So AD is equals to DB. This implies that P lies on the perpendicular bisector of AB. P lies on the perpendicular bisector of AB. So what we did was, it was given that PA is equals to PB. We have to prove that P lies on the perpendicular bisector of AB. So given any point in the plane, you can drop a perpendicular from that point to the line. Yes, you can drop a perpendicular from any point to that line if the point is not lying on that line. So similarly, we dropped a perpendicular from P onto the line segment AB, and if we dropped a perpendicular from P to the line segment AB, we saw that this perpendicular divides the line segment AB into two equal halves, right? Dropping the perpendicular from P on the line segment AB, we observed that this perpendicular divided the line segment AB into two equal halves. So then we were assured that P must lie on the perpendicular bisector of AB. So what can we say is that every point on the perpendicular bisector of AB is equidistant from A and B, and if there is any point which is equidistant from A and B, it must lie on the perpendicular bisector of line segment AB. Okay, so these statements are true. Both the statements are true. Okay, so by combining both the statements, I can say that P lies on perpendicular bisector of AB if and only if P is equidistant from A and B. P is equidistant from both A and B. So what do you mean by if this sentence if and only if? So if and only if means that the statement is true both ways. That is, if P lies on perpendicular bisector of AB, then I can say that P is equidistant from A and B. And if P is equidistant from A and B, then I can say that P lies on perpendicular bisector of AB. So this is the meaning of if and only if. So let us just understand what this if and only if means in detail, because this is a very basic but very important concept. So say you have x is equals to 2, then you can imply that x square is equals to 4, right? So x is equals to 2 is a statement, x square is equals to 4 is another statement. And what do you mean by implies? Implies means that it is a statement of the type if A then B. Okay, so this is a conditional statement. This is a conditional or implicational statement. Okay, so if A then B, you can write it as A implies B. So in this case, x is equals to 2 implies x square is equals to 4. This means that if x is equals to 2, then x square is equals to 4. So this I have written it in English, and this is nothing but mathematical notation. Okay, so x is equals to 2 implies x square is equals to 4, and the same way of writing this in English is if x is equals to 2, then x square is equals to 4. So this is the general format of conditional or implicational statement. If A then B, where A and B are simple statements, this in mathematics can be written as A implies B, or A implies B means that if A then B. Okay, so let us see some more examples. Say if x is equals to 2, then I can say that x plus 3 is equals to 5, right? So in mathematics, I can write this in this way. X is equals to 2 implies x plus 3 is equals to 5. This is perfectly true. Okay. So the difference is that A implies B need not imply. Okay. Just a second. Say if A implies B is true, then B implies A need not be true. Okay. If A implies B is true, then B implies A need not be true. For example, x is equals to 2 implies x square is equals to 4. This is a true statement, right? But x square is equals to 4. This implies x is equals to 2. This is not true statement. This is a false statement. Why? Because x square is equals to 4 doesn't necessarily imply x is equals to 2. Okay. It may so happen that x may be minus 2. Okay. So x may be minus 2. So x square is equals to 4 implies x is equals to 2 is a false statement. But x is equals to 2, then I can definitely say that x square is equals to 4. So this is a true statement. Whereas if x square is equals to 4, then I definitely can't say that x is equals to 2 because x might be minus 2 also. So I'm not sure. So this statement is a false statement. So it means that I can use this implication sign in only one direction, not in the reverse direction. But say if let us consider another example. X is equals to 2 implies x plus 3 is equals to 5. This is a perfectly true statement because whenever x is equals to 2, definitely x plus 3 would be 5. And I can also say that x plus 3 is equals to 5 implies x is equals to 2. This is also a true statement because whenever x plus 3 is equals to 5, then I can definitely say that x must be 2. There is no other possibility. So both these statements are true statements. So then I can write that x is equals to 2 by implies x plus 3 is equals to 5. By implies means both the statements are true. That is x is equals to 2 implies x plus 3 is equals to 5. This is true. And x plus 3 is equals to 5 implies x is equals to 2. This is true. This statement is true in both the directions. So here we can use this sign by implication or by conditional sign. And in English we write it in this way. We can write this as x is equals to 2 if and only if x plus 3 is equals to 5. And if and only if, you can write it in this way also, I double f. So x is equals to 2 I double f, x plus 3 is equals to 5. So both these things are equivalent. So if and only if, you can also write it as I double f. So this is what we have done in English. And in mathematics, you write it in this way. This is the notation for by implication. That x is equals to 2 implies x plus 3 is equals to 5. And x plus 3 is equals to 5 implies x is equals to 2. So this statement is true in both the directions. And this is the English way of writing this statement. So you just copy these things down. So I'll give you 30 seconds, copy these things. Yeah, copy this thing also. Just quickly copy it and we'll move further. Okay. Also, yeah, note down this problem also. Copy this one and you can note this important statement that P lies on perpendicular bisector of AB if and only if P is equidistant from A and B. Fine. So let us move further. Okay. So let us come back to our geometry. So now, say if P is equidistant from two line segments AB and AC, then prove that P lies on the angle bisector of these two lines. These two lines, right? That is angle bisector of angle BAC. So just try this question, draw the diagram and prove it using the congruencies. So 30 seconds for this. Okay, so let us do this. So there are two line segments here, AB and AC. So let us say this is AB and this is AC. Now P is equidistant from these two lines. Okay, so let us say there is a point P. This equidistant. What do you mean by distance of a point from a line? So it is nothing but the shortest distance or the perpendicular distance. This is the distance of point P from line AB. This one is the distance of point P from line AB. And this is the distance of point P from this line AC. So let us call this point as say D and let us call this point as say E. Okay. So it is given that P is equidistant from two line segments AB and AC. It means P, the distance of P to AB is equal to the distance of P to AC. So it means that it is given that PD is equals to P. So it is given that PD is equals to P. That is P is equidistant from these two lines AB and AC. And now we need to prove that P lies on angle bisector of angle A. So let us join AP. Okay, let us join AP. So if I join AP, then I can see that these two triangles are congruent. That is the triangle PAD and the triangle PAE. These are congruent because there is an angle which is equal to 90 degrees and the hypotenuse is the common side, so this is equal. and it is given that PD is equals to PE, that is the P is equidistant from two line segments AB and AC. So I can see that triangle PAD is congruent to triangle PAE by right angled hypotenuse and side congruency. So then what can I say? Then I can say that angle PAD must be equal to angle PAE because the corresponding angles must be equal. So angle PAD is equal to angle PAE. So this means that AP is the angle bisector, right? AP is the angle bisector of lines, or you can say line segments AB and AC. Okay, so this means that P lies on the angle bisector, right? P lies on the angle bisector of AB and AC. Okay, so quickly copy this, then we'll move forward. So if P is equidistant from two line segments AB and AC, then P lies on the angle bisector of AB and AC. Okay, let us move forward. Let us prove the converse of this statement. What would be the converse of this statement? The converse is simple, that if P lies on angle bisector of AB and AC, then we need to prove that P is equidistant from AB and AC. P is equidistant from AB and AC. So this is the converse. Okay, so 30 seconds to try this one, then we'll discuss. Fine, so let us discuss this one. It is given that P lies on the line angle bisector of the line segments AB and AC, right? So this is the angle bisector. So this is a point P. We need to prove that P is equidistant from these two line segments. So this is point D and this is point E. So we need to prove that PD is equals to PE. This is what we need to prove. Fine. So we'll use the congruency of triangles again. Okay. So if you see these two triangles PAD and the triangle PAE, you can see that these two angles are equal, and this is a right angle which is equal, and AP is the common side. So by AAS criterion, these two triangles are congruent. So the triangle APD is congruent to triangle APE by AAS criterion. So this implies that the corresponding sides, that is PD, must be equal to PE. Okay. So then it is proved, right? So if P lies on angle bisector of AB and AC, then P must be equidistant from AB and AC. So from the previous two statements, what can I say? That this is an if and only if statement, right? That is, if or say I can write it in this way. P lies on the angle bisector of AB and AC if and only if. Now instead of writing if and only if, I'm just writing IFF if. So if and only if P is equidistant from AB and AC, right? So this is also an if and only if statement. If there is any point which is equidistant from AB and AC, then it must lie on the angle bisector, and vice versa is also true. That is, if there is a point which is on the angle bisector, then it must be equidistant from those two lines. Okay, so just quickly copy it down, then we'll move forward. Fine. So let us move forward. So what we have proved until now is that if there is any point which lies on the perpendicular bisector, then it is equidistant from those two points and vice versa. And if there is any point which lies on the angle bisector of two lines, then it is equidistant from those two lines and vice versa. Okay. So now let us move forward. Now we will prove that in any triangle, the perpendicular bisectors of three sides are concurrent. The perpendicular bisectors of three sides are concurrent. Okay. So let us say there is a triangle ABC. Fine. We need to prove that the perpendicular bisectors of all the three sides, that is AB, BC and AC, they meet at single point. That is, they all pass through a single point. And we already know that that point is called the circumcenter of triangle ABC. So let us do this. What I'm doing is, I'm drawing the perpendicular bisector of any two sides. Say I'm drawing the perpendicular bisector of BC and AC. Okay, so this is the perpendicular bisector of BC and AC. So let us say they meet at point S. Okay, so draw perpendicular bisectors of BC and AC to meet at point S. Fine. So this is what I have done, right? Because any two lines can definitely intersect at one point. There is nothing special in that. But if a third perpendicular bisector, say the perpendicular bisector of AB, this also passes through the point of intersection of first two perpendicular bisectors. This is what we need to prove, right? That is, the perpendicular bisector is not this, it is not this, it is not this. These are all not the perpendicular bisectors. Only this can be the perpendicular bisector. This is what we need to prove, it, right? So I have assumed that the perpendicular bisectors of two sides, that is BC and AC, they intersect at point S. Now what I will do is, I will prove that the perpendicular bisector of AB must also pass through S, right? I have assumed that perpendicular bisectors of the sides BC and AC, they intersect at point S. Now I will prove that the perpendicular bisector of AB must also pass through point S. Then I have proved that all the three perpendicular bisectors must pass through the same point S, so they are concurrent. Okay, so that is our aim. We are aiming to prove that the perpendicular bisector of AB passes through point S, or I can say that the point S lies on the perpendicular bisector of AB. This is our aim. Okay, so let us clearly write what is our aim. Aim is to prove that the same point S also lies on perpendicular bisector of AB. So this is our aim. Okay, let us prove it. So, okay, instead of me proving, I'll just give you a couple of minutes to try this, then we'll discuss. Okay. So I have clearly stated what is the problem statement. So we have drawn the perpendicular bisectors of BC and AC to intersect at point S. Now we need to prove that this S also lies on the perpendicular bisector of AB. This is what is our aim. Okay, so just use the previous 3-4 questions which you have did to do this. So we'll discuss after a couple of minutes. Fine. So let us discuss this one. So since the point S lies on the perpendicular bisector of BC, okay, since S lies on perpendicular bisector of BC, I can say that SB is equals to SC, right? Because if any point lies on the perpendicular bisector, it is equidistant from those 2 points B and C. Similarly, since S lies on perpendicular bisector of AC, this implies that SA is equals to SC, right? That is, S is equidistant from A and C, and SB is equals to SC means S is equidistant from B and C. So from these two equations, that is the equation 1 and equation 2, I can say that SA is equals to SB, right? Because SC is equals to SB and SC is equals to SA. So these two must be equal. Now, since SA is equals to SB, that is, S is equidistant from both A and B, this implies that S lies on perpendicular bisector of AB, right? Because we have already discussed that if there is any point which is equidistant from A and B, then that point must lie on the perpendicular bisector. So since S is equals to SB, I can say that S must lie on the perpendicular bisector of AB. Okay. So this was our aim, to prove that S lies on perpendicular bisector. So what we have done is to prove that the perpendicular bisectors of 3 sides are concurrent. We assume that perpendicular bisectors of any 2 sides intersect at some point, say S, and then we proved that the perpendicular bisector of other side, that is AB, must also pass through S, or we have proved that this S must lie on the perpendicular bisector of AB. So we have proved that all the 3 perpendicular bisectors must pass through the same point, so they are concurrent. Okay, so just quickly copy this down, then we'll move further. Fine. So let us move further. Now, what we'll try to do is we'll try to prove that internal angle bisectors of any triangle, internal angle bisectors of the three angles of any triangle are concurrent. So the internal angle bisectors of three angles of any triangle are concurrent. So say there is a triangle ABC. Okay. I need to prove that the bisectors of angle A, angle B and angle C are concurrent. That is, they pass through same point. So what I will do is I will draw the angle bisectors of any two angles. Say I'm drawing angle bisectors of angle B and angle C. And let us say these two angle bisectors intersect at point I. Now I will prove that this I also lies on the angle bisector of angle A, or in other words, this angle bisector of angle A must pass through I. This is what I have to prove, right? I have assumed that the angle bisectors of angle B and angle C intersect at some point, say I. We know that it is an in-center. And now we'll prove that the angle bisector of angle A must also pass through this point I, same point. So then we will be proving that the angle bisectors are concurrent. Okay. So draw angle bisectors of angle B and angle C to intersect at point I. Okay. Now our aim is to prove that I also lies on angle bisector of angle A. So just try this for a minute, then we'll discuss. Angle bisector of angle A. So we'll discuss this after a minute. So by the same things which we have discussed in the starting of this session. Fine. So let us discuss this one. So since I lies on the angle bisector of angle B, so I is lying on the angle bisector of angle B, it means that I is equidistant from the line segments BC and AB, right? So let us say this is the perpendicular from I to BC and this is the perpendicular from I to AB. Say this point is D and say this point is F, and say this is the perpendicular from I to this side. So this point is say E. Okay. So since I lies on angle bisector of angle B, so since I lies on angle bisector of angle B, this implies that I is equidistant from AB and BC, right? So this means that ID is equals to IF. And similarly, since I lies on the angle bisector of angle C, this implies that I is equidistant from these two lines. That is, IE is equals to ID. So IE is equals to ID. So now from these two equations, I can say that IE is equals to IF, right? That is, I is a point which is equidistant from AB and AC, right? So what do you mean that I is equidistant from AB and AC? This simply means that I must lie on the angle bisector of angle A, right? So this implies that I lies on angle bisector of angle A, right? So we have drawn the angle bisector of any two angles, right? They can definitely intersect at some point, say I. Now we have proved that the angle bisector of the other angle also must pass through this point. So we have proved that these three angle bisectors must be concurrent. That is, they all pass through the same point I. Okay. So let us discuss what is an incircle here. So since I is equidistant from the sides of the triangle, right? Because ID is equals to IE is equals to IF. So since these 3 points, that is E, F and D, these are equidistant from I, right? So I can definitely draw a circle which is passing through these 3 points, right? And that will be equidistant from the center of that circle must be I, because IE is equals to IF is equals to ID, right? So this circle is called the incircle of triangle ABC. Okay. So since I is equidistant from the sides, so with I as center and ID or IE or IF as radius, if I draw a circle, I'll get a circle which is called the incircle of triangle ABC. And this incircle touches all the three sides. That is, it touches the BC, AC and AB. So this is the incircle of triangle ABC. And what is the radius of this incircle? The radius is ID or IE or IF. This is the radius of incircle. Okay. So similarly here, what we have observed is that the circumcenter S, it is equidistant from three vertices of triangle. That is, it is equidistant from A, B and C, right? That is, SA is equals to SB is equals to SC. So since SA is equals to SB is equals to SC, I can say that if I draw a circle through these three non-collinear points, right? If I draw a circle through A, B and C, then the center of this circle must be S, because SA is equals to SB is equals to SC, right? Or if I draw a circle with S as center and SA as radius, then this will also pass through B, because SA is equals to SB. So SB is also the radius. And similarly, this also passes through vertex C, because SA is equals to SB is equals to SC. So SC is also the radius. So if I draw a circle with S as center and S as radius, right, then this circle will pass through all the three vertices of triangle ABC, and this circle is called the circumcircle of triangle ABC. Okay, fine. And what is the circumradius of this triangle? SA or SB or SC. These are the circumradius of the triangle. All are equal, right? So SA is the circumradius of this triangle, and this circle which passes through all the vertices of triangle is called the circumcircle of triangle ABC. And the circle which touches all the sides of a triangle is called the incircle of triangle ABC. And the center is in center. And the radius is ID or IE or IF. Fine. So just copy it down quickly and move further. Copy it down quickly, then we'll move further. Fine. So let us move further. Now, let us prove that the altitudes in any triangle are concurrent. So prove that altitudes in any triangle are concurrent. Means they pass through same point. Okay. So let us say we are given a triangle ABC. Fine. So the altitudes, what is an altitude? Altitude is one which is drawn from vertex of a triangle so as that it is perpendicular to other side, that is BC. So a line segment drawn from vertex of a triangle perpendicular to opposite side is called an altitude of a triangle. So AD is the altitude, BE is the altitude, and CF is the altitude. Fine. So we need to prove that these all altitudes pass through the same point, and we know that that point is called the orthocenter H of the triangle ABC. Okay. So what I'm going to do is, just a second. So what I'm doing is I'm drawing a line through A. I'm drawing a line through A which is parallel to BC. Okay. So this is parallel to side BC. I'm drawing another line through C which is parallel to AB. Okay. So this line is parallel to AB. And I'm drawing another line through B which is parallel to AC. Okay, so this is parallel to AC. Okay, so let us say these points of intersection which we have obtained are points D, E, and F. So what I have done, draw lines through A, B, and C which are parallel to BC, AC, comma AB respectively. This is what we have done. Okay, so we have drawn lines through all the vertices of triangles which are parallel to the opposite side. That is, this line DE is parallel to BC, this EF is parallel to AB, and this DF, this is parallel to AC. Okay, so this is what we have done. Now let us observe this figure or this quadrilateral, that is the quadrilateral AEBC. Okay, if you observe the quadrilateral AEBC, you can say that these two are parallel and these two are parallel, right? So since both the opposite sides are parallel in quadrilateral AEBC, then I can say that this quadrilateral is a parallelogram. Similarly, this quadrilateral ADBC is a parallelogram, right? So quadrilateral AEBC and ADBC are parallelograms, right? Because both pairs of opposite sides are parallel. Fine. Okay. So now if these two are parallelograms, then I can say that AE is equals to BC and AD is equals to BC, right? AE must be BC because the opposite sides are equal in a parallelogram, and AD must be equal to BC, right? So that is that I can say that A is the midpoint of side DE because these two are also equal, right? This implies that AD must be equal to AE. So we have proved that A is midpoint of DE, and AD is definitely perpendicular to BC, right? AD is perpendicular to BC because it is an altitude. So DE is parallel to BC and AD is perpendicular to BC, then AD is also perpendicular to DE, right? Since AD is perpendicular to BC and DE is parallel to BC, this implies that AD is also perpendicular to DE. Fine. So since AD is equals to AE, or this implies that A is midpoint of DE. Okay. So since A is midpoint of DE and AD is perpendicular to DE, what can I say about AD? AD is the perpendicular bisector of side DE, right? So say this is equation 1 and this is equation 2. So 1 and 2 implies that AD is perpendicular bisector of side DE of triangle DEF, right? So what I have said is AD is the perpendicular bisector of this side DE, right? This is what we have proved until now. So in a similar fashion, I can prove that CF is the perpendicular bisector of this side EF and BE is the perpendicular bisector of this side DF, right? So similarly, so this is the symbol for similarly, 3 L's and Y. Similarly, this side BE is the perpendicular bisector of DF and CF is the perpendicular bisector of EF, right? So CF is perpendicular bisector of EF and DE is perpendicular bisector of DF, right? So you can see that in this triangle DEF, this BE is perpendicular bisector. Just a second, this is BE, not DE. So in this triangle DEF, you can notice that BE is the perpendicular bisector, CF is the perpendicular bisector, and AD is the perpendicular bisector. So just now we have proved that the perpendicular bisectors of 3 sides in any triangle are concurrent. So the perpendicular bisectors of this triangle DEF must be concurrent, right? So perpendicular bisectors of triangle DEF are concurrent, right? So since the perpendicular bisectors of triangle DEF are concurrent, this implies that AD, BE and CF are concurrent, right? This implies that altitudes of triangle ABC are concurrent because this AD, BE and CF are altitudes of triangle ABC. These are concurrent. Okay. So what we have done, we have drawn lines through A, through B and through C parallel to the opposite sides of triangle, and then we have observed the parallelograms in the figure, and finally we managed to prove that this AD, BE and CF are nothing but the perpendicular bisectors of this triangle DEF. So these must be congruent, concurrent. So then I can say that AD, BE, CF, which are the altitudes of triangle ABC, must be concurrent. And we know that this point of concurrence is called orthocenter H. Okay, so this is called orthocenter and it is denoted by capital H. Okay, so this triangle ABC is called the medial triangle of DEF, right? Since B is the midpoint of DF, A is the midpoint of DE, and C is the midpoint of EF, right? So if you draw a triangle by taking the midpoints of any all the 3 sides, then that triangle is called the medial triangle of original triangle. That is, ABC is the medial triangle of triangle DEF. Okay, so quickly copy this, then we'll move forward. Quickly copy this. Fine. So just try to do all